Thank you everyone for attending today's Tools and Tech seminar. My name is Jie Cao. Today I'm going to give a talk on building a software pipeline for developing and evaluating time series machine learning models using electronic health record EHR data. So a little bit about myself. So I got my Bachelor of Science in Biotechnology in 2013, and then I came to University of Michigan School of Public Health, obtained my Master of Public Health in Epidemiology. Then I have 3 years of work experience and joined the PIPS DCND PhD program in 2018. So I'm in my 3rd year of my PhD life. Currently, my dissertation thesis is mentored by 2 professors, Dr. Karandeep Singh, who leads the Machine Learning for Learning Health Science lab, and Dr. Keval Najarian, who leads the Biomedical and Clinical Informatics lab. This is Dr. Singh, and this is Dr. Najarian. And my research interest and focus lies in clinical predictive modeling using EHR data. And we are particularly interested in bringing models to bedside. So the packages I'm going to talk about in today's presentation is developed in Machine Learning for Learning Health Science lab. The major contribution is from Dr. Karandeep Singh. Okay, so let's first talk about the EHR data. In 2009, President Obama signed the Health Information Technology for Economic and Clinical Health Act into law to promote translation to EHR and the health information exchange. Starting in 2011, an incentive program was developed and led by CMS to promote meaningful use of EHR nationwide. This figure shows here shows that as of 2016, over 98% of US hospitals have participated in this system. And here at Michigan, we are 100%. And when we use EHR data to develop clinical models, there are typically 2 types of predictions we can make. One is one-time prediction. This is very basic and typical. For example, we can predict a patient's 7-day mortality at their time of admission, or we can predict their 30-day readmission at the time of they are discharged from the hospital. And this kind of prediction task is very similar to what we learned and practiced in many statistical learning, machine learning courses, because it only does one-time prediction and it's very simple. But in clinical practice, what clinicians really care about is to do some sequence prediction, so that we can monitor patients' health status continuously during their hospitalization. So in the figure here, the top panel shows patient creatinine measurements during the patient's hospitalization. Creatinine is used in nephrology as a biomarker and important measurement to diagnose patients' kidney disease. For example, the acute kidney injury I marked here. And ideally, clinicians want such an algorithm that can give continuous prediction of patient risk. And in an ideal case, the algorithm can predict a patient's risk of getting the disease in a lead time prior to the onset of the disease. Like the bottom panel here shows the model predictions given by an algorithm, and it captures patients' elevated risk of having AKI earlier than the real AKI, where AKI really occurs. So this kind of sequence prediction is what I'm going to focus on in today's talk. And then let's look at what kind of challenges exist in EHR data analysis. The raw EHR data has very special characteristics. First, it is a mixture of fixed data and the temporal data. Here, this graph shows some example tables that are components of EHR database. For the fixed data, that means the variables, the features that does not change as time goes by. For example, the patient demographics, like the sex, race, ethnicity. But for certain variables like the age, although it can change as time goes by, but usually in prediction task in a rather short period, we can also consider it to be fixed data. And the temporal data are time series data. They are something like lab results, medicine. They are stamped by a time point during patients' hospitalization, and their values are continuously checked and changed during patients' hospitalization. And for temporal data, it's a little bit complicated. In EHR data, it's usually stored in a long format, like the example table here. When I say a long table, it means one patient can have multiple rows, and each row is stamped by a time point and only displays one event and a value associated to it. So you can imagine how long this table can be for all the patients in our system, in our EHR system. And unlike this temporal data is unlike data we collected from a design study. In a designed research study, we can design to collect certain measurements in regular intervals. But in EHR data, because this is real world data, usually it's the consecutive data points have irregular intervals, like the figure shown here. And to make the table more intuitive to our human beings, usually we want the data to be reorganized to this way. Each row represents one patient's status, and it can have fixed data and temporal data. And for temporal data, there's a critical need to transform them into a more cleaned way so that it can be used as input for machine learning models. For example, we talked about these data points are collected irregularly. And a common practice is that we prepare these longitudinal patient data, aggregate them using some summary statistics so that they can have a fixed length of feature vector. So no matter how many data points in this observation window differs from the next observation window, we always have a fixed length of feature vector so that we end up with tabular data. So this is the first challenge we find in our EHR data analysis. So there's a need for data transformation tools. So the next challenge is that EHR data typically contains both structured data and unstructured data. Most of us are more familiar with structured data, like this tabular data, demographics, vital signs, even the temporal data, medication, lab results, they are structured. But many of the medical information are contained in unstructured data, like the clinical notes, and the images and the videos, they are also unstructured data. So we next identify that there's a need for clinical text processing tools. In clinical natural language processing, specific tools are required to complete the following typical clinical notes NLP tasks, like named entity recognition, medical concept mapping, negation, detection, sectionizer. So the idea is that we want to convert this kind of unstructured data into structured data format so that they can be used for machine learning algorithms. And currently, there are many existing clinical NLP tools in Python, and we see that there's a need for similar clinical NLP tools in R. And lastly, we also find that there is a need for clinical predictive model evaluation tools. So when evaluating a clinical predictive model, there are different aspects you need to take into account. The first one is discrimination. So discrimination means how well the model can discriminate a data with outcome from with outcome. And most often, you will see AUC as a single metric used to compare models to show the model performance. But we also see there's some pitfalls about AUC. So first, there's no threshold information if you only look at AUC. And although you can plot the ROC curve to show the sensitivity, specificity, how they change as at a different threshold, we still think there's limited ability to compare models conditional on threshold using a ROC curve only. And because it only shows sensitivity and specificity, it can potentially provide you misleading information. The second aspect people will look at model performance is called calibration. Calibration shows you the agreement between predicted probabilities and observed probabilities. I'll talk about it in details in a later slide when I talk about our package about model evaluation. And lastly, once you know your model has good discrimination, good calibration, there's some decision you need to make to bring it to bedside. For example, given a model, there are many thresholds you can choose. And for your practice, what is the optimal threshold that you want to choose? And at this chosen threshold, what is the net benefit you can get using this model? So based on my review of the background information about EHR and the gaps we identified, so in our lab, we have developed 3 tools. One is to transform EHR data for machine learning training purpose. It's called a Wizard. Next is to help researchers handle clinical text processing using R. The third is to, the NLP tool is called CleanSpacey, and the third one is used to evaluate and compare prediction models. We call it runway. So I have the links here. So you are free, just feel free to search it on GitHub, and we have tutorials for each of the package. And due to the time limit, there's more background information you will need to understand NLP tasks. Today, I'm going to just focus on the data transformation tool Wizard and evaluation tool Runway. Yeah, but just feel free to contact me for the NLP package. I'd be happy to answer questions offline. So let me first talk about the Wizard package. Wizard is abbreviated for Windowed Summarization for Autoregressive Data. So in this package, we provide the following functionalities. Our package can help you transform your EHR data in the following ways. First, it can help you segment hospitalizations into time steps. Here I use hospitalizations because this is the typical time range we will use in clinical predictive modeling, but you are welcome to define your own start and end time in our package. Next, after the hospitalization is segmented into steps, the package can help you create rolling prediction and outcome intervals of varying lengths and calculate the associated rolling statistics. So in our package, we provide you sample data set for you to play with. And you can also provide your own data. The only requirement is that you provide one version of fixed data and one version of temporal data, like I mentioned before in the background slides. And these two screenshots are the sample data we provided. We provide with our package, and they are made up, so there's no sensitive information. So just be assured. Okay, so the first thing our package can do is to help you cut the temporal data into steps. I use a graph to illustrate the process. Say this is when the patient is admitted to the hospital, And like I mentioned before, we want the algorithm to predict a patient's risk of having the disease every couple hours. Say like here, we want to ask the algorithm to predict the risk every 6 hours. There you define your step to be 6 hours. This is the first step. And here, you just design your wizard frame, provide your fixed data, temporal data, start, end time, the ID, and the step. Yeah, and you can also ask the function to write the output to your specified directory. And next one is a little bit complicated. So for each step, we would like to generate predictors and outcomes. And there are several concepts associated with them. They are window size, look back, and look ahead period. And you also need to define summary statistics. So I also use the graph to illustrate. Say we want to make a decision, make a prediction at this time point, like 12 hours after the patient is admitted to the hospital. And we want to predict a patient's risk of having the disease 24 hours later. So this is where we are, this is what we are going to predict. So this period, we call it a look ahead period. And the information you want to utilize, we call it a look back period. Say if you want to pass the 48 hours data, then you just say your look back period is 48 hours. Because in some prediction tasks, you may use a longer time of look back period, and you might want to break down your data into smaller granularity. So we provide another option for you to define your window size. Say if you want to go back 48 hours, but you want to extract a 6-hour window of data separately so that you can put more weights on the more recent 6-hour data. So that's also possible using our package. And for each window, you can supply the summary statistics you want to use for this window. And as time goes by, let's move to next time step. And again, we want to predict 24 hours later whether the patient has risk, and the same look ahead, look back, and window size. And next step. So just imagine how many times you are gonna do this kind of process again and again. And given that EHR data has very large size, this data preparation can be really tedious. But with our package, you just call the with add predictors and the with add outcomes, tell them the variables, look back, look ahead period, and the summary statistics. For predictors, there can be different ways to calculate predictors. And so we offer some more specific type of predictors that you can utilize. Yeah, so just by calling these functions, you will get this list of files in your specified directory. And with these data, you can supply them into model. But there's one last step you need to do because they are in separate files. And our package can also help you to combine them to form a single data set for model input. Just call it with combine, and you'll have this final data set ready for model development. So in this final model data set, you have fixed data. You also have temporal data. And this is the step we defined before, meaning every 6 hours, we are going to make a prediction. And for every step, this is one row. This row is the data you are going to use. This is the outcome variable. These are all the predictors you can use. Yeah, So this just makes EHR data preparation easier in our lab. And another thing I want to mention is because EHR data is large, usually enabling parallel processing can speed it up. So it is also possible with our package. You just need to call plan multi-session from the future package at the beginning of your script, and it can process the data preparation in parallel. And we provide the benchmark results here. These two results are using multi-session, and this one is just sequentially preparing the data. And you can see that the model speed is faster with the multi-session. So this wraps up my tutorial about our wizard package. The next package I'm going to introduce is called runway. This package is designed for evaluation and a comparison of prediction models. So why is it called runway? I think you may have this experience that sometimes your model just look quite different. It's very easy to tell which one is the best to use, and you're like, oh, whoa, I'm done. I know what I'm gonna do next. But other times you may see your models look the same, especially when you are using very simple or single metrics to compare different models. So we hope that with our package, you will be able to like walking on the runway and say, oh, I'm excited. I know the model. I know which model is great. For this package, the input data we require is very simple. If you are just looking at a single model, you just supply two columns. One column is the true labels of your data, and the other column is the predictions given by your algorithm. And you can also compare different models. The only thing you need to add is another column indicating which model it belongs to. So these two are also screenshots of our sample data provided in our package. So the first thing I'm going to talk about is discrimination. Like I mentioned before, people usually use AUC to represent the discrimination of a model. But here we propose to use this threshold performance plot. It is a form panel plot with a histogram and showing the threshold from 0 to 1. And what's good about this kind of plot is that it carries all information of an ROC curve because it provides the sensitivity and the specificity. And also in clinical modeling, we often plot a precision recall curve together with ROC curve. Precision recall curve is just a positive predictive value versus sensitivity curve, because clinicians want to use this kind of curve to have a sense of false alert, because PPV typically tells you what's the proportion of true positives out of the predicted positives. If that proportion is low, that means the clinicians need to evaluate a lot more patients to get a true positive. So this is also very helpful in clinical predictive modeling. And also in our plots, we provide the distribution of the predictions to give you a sense like how it is distributed. And we also, in these two shaded area, shows at a given threshold, what is the proportion of positives and the negatives given by the algorithm. So we think this this kind of threshold performance plot gives you a lot of information in one plot, and you can pick whichever you are more interested in. You want to focus more on just from this plot. And we also enable our package to compare performance between different models using this function. And here is an example. And the next thing we will look at for a clinical predictive model is the calibration. The idea of calibration is to tell you the consistency between the predictive probability versus the observed probability. When a model is calibrated, we are confident to say that the probability value given by the algorithm can be appropriately interpreted as probability because it is consistent with the observed probability. Let me use an example. Say for a group of 100 patients, the average predicted probability given by an algorithm is 0.4. Let's say it's 0.4 for these 100 patients. And if this value can be interpreted appropriately as a probability, that means we would expect to see 40 out of 100 patients actually have the disease. So what we want to do is that we pull the true labels and count how many out of these 100 patients actually have the disease and plot them on the y-axis and compare to the x-axis predicted probability. And ideally, a well-calibrated model will align with this diagonal line very well. But if a data point is below the diagonal, it means that your model is over predicting the risk probability. And in contrast, if the data point is above the diagonal line, that means the probability given by your model is under predicting the risk. Calibration plot is an important metric to look at because nonlinear machine learning algorithms often predict uncalibrated class probability. So you should be cautious when calling them class probabilities or interpreting them. And similar to the discrimination plot, you can also compare the calibration plot for multiple models like the one shown here. Next, I'm going to talk about the application of our runway package in a study we did last year for COVID-19 patients. So this is a study we did for adult patients admitted with COVID-19 to non-ICU level of care at Michigan Medicine. The data is from March 9th to May 20th last year. And we want to predict a composite adverse outcome, including ICU level care, mechanical ventilation, or death. And because that's in the very early phase of the pandemic, there's no existing algorithm designed for COVID-19 patients only. So we were thinking that can we use some existing models to do such predictions and maybe repurposing it, or at least the model can provide us some information. So we found the EPIC deterioration index model. It is a model developed by EPIC and also embedded in the EPIC system, which is the EHR system we are using at Michigan Medicine. It runs at the back end, and every 15 minutes, it gives you a deterioration index ranges from 0 to 100 for an inpatient patient. We were hoping that we could use such model to identify patients with high risk of experiencing this composite adverse outcome or low risk of adverse outcome. This is critical because in early pandemic, the resources are very limited. So we hope this kind of algorithm can help us prioritize resources. And also, this paper can serve as an example how we do model repurposing and model evaluation on a different cohort. So we like I mentioned in the previous slide, we did two kinds of analysis. One is high risk analysis. We want to see whether this index can identify patients with high risk of experiencing adverse outcome or versus non-high risk analysis. And another analysis is to predict a low risk versus non-low risk. And for the high risk analysis, we examine the threshold from 0 to 100 and compare the performance of 4 different metrics at each threshold. And clinicians picked this threshold. It's 68.8, meaning if in the system, this model gives an indexed value of 68.8 or greater for a patient, then we say this patient has high risk of experience adverse outcome. And at this threshold, we see that the positive predictive value is 74%. And this means that for clinicians, they need to evaluate 1.4 patients to find one true deteriorating patient. And at this threshold, the sensitivity is 39%, not high, but better than not having a model. And for the low risk analysis, the cohort is a little bit different. So we only include patients who had not been discharged or experienced the primary outcome at 48 hours. So the cohort is a little bit smaller than this one. That's why you'll see the plot is a little bit different from this one. And for low risk, we examine the thresholds and use the threshold of 37.9. And if the patient index is less than 37.9, we think this patient has low risk of experiencing adverse outcome for the remainder of their hospitalization. And you'll see that the negative positive value, the negative predictive value is 90%. Yeah, so that means the 90% chance of this patient is true low risk among all the all we predicted negative patients. And here we capture the sensitivity of 91%, meaning we capture the 91% of true high risk patients. So we use these kind of plots to give audience a sense of the overall performance of the model. I think for clinicians, this plot provides almost everything they want and need to look at a model's discrimination, especially this distribution of predictions. And like I mentioned before, a calibration plot is also critical for this analysis. This is the calibration plot we got. So you'll see that all the data points are below this diagonal line, meaning that this deteriorating index is over predicting the risk of having the disease. So when you say, here we convert range, the index, it ranges from 0 to 100. We convert it to 0 to 1. So when you have 0.3 here, we convert it back to index of 30. So when you have a patient of index equals to 30, it's not safe to interpret that the patient's risk is 0.3 because this index is over predicting the risk. So this is something you need to be cautious when interpreting it. And we would say this model is not very well calibrated for this population. Here is another set of figures we made to show how early this kind of alert can capture patients' high risk. So every dot here shows the alert for high-risk patients given by the algorithm, and the red dot represents the first alert that was generated. So we see that the median lead time from when the threshold was first exceeded to when the outcome occurred was 24 hours. And we have a zoom in for these patients and showed where their first alert was generated. So the conclusion we have for this paper is that the epic deterioration index can be repurposed to evaluate the risk for COVID-19 patients to some extent, but it is better than nothing. It is better than having no model, but the results should be interpreted carefully, and more efforts is needed to calibrate this model, further development of this model, or design a new model for COVID-19 patients. And we are still developing our runway package, and there are some more things we are considering to add to this package. The first thing is that we want to make interactive version of the plots, so that when you hover over your mouse onto the plot, on the plot, you can see the exact value of threshold and the exact value of different metrics. Alert timeline is what I showed in the previous slide. The red dots represents the first alert, and the rest of the alerts are in black dots. So we got very good feedback from clinicians that this can be helpful to give you a sense how the model would work in the real life. So we are considering adding it to the package. And another thing I mentioned in the background slides, but has not been implemented in our model, is the decision curve. So the idea of decision curve is shown in the figure here. So basically, you want to look at the net benefit comparing different models and different interventions. Say this is the dashed line, we call it a test. You can think of as a standard clinical practice. It's like a diagnostic test. And this is a net benefit given by the statistical model we developed. And we need to compare them with two references. One reference is called an intervention for none, meaning we just don't intervene any patient. Another one is called intervention for all, meaning we just assume everyone has the problem and intervene everyone. So we know they are not best strategy, but they can use as baseline for comparison. And what net benefit plot the decision curve gives you is that you can compare the net benefit of model compared to these two baseline, and you can also compare to a standard test or other statistical models to see at your given threshold whether your model exceeds all other practices or other models. And if that's the case, it's an evidence that your model is likely to benefit in clinical practice, and you can use this as an evidence to tell people, yes, we should implement this model. So as a summary, in our lab, we carefully examined the challenges for the EHR data analysis, and from the data preparation, clinical notes processing, and the model evaluation and the comparison, we have developed 3 packages. First, the wizard to handle the data transformation for the unstructured data. The clean spacey, you can use it to complete certain clinical NLP tasks. And lastly, runway can help you do a comprehensive evaluation and the comparison of the prediction models you have. So together, we build a data pipeline for time series electronic health data analysis in machine learning tasks. So we hope this talk can help everyone else interested in EHR data a little bit. And if you are interested in talking more details about the package and need some help, just feel free to contact me offline or just throw a question here at the seminar. Yeah, that's the end of my talk and my reference. So if you have any questions, feel free to ask.
It's really a great job, Jie. We really enjoyed that.
Thank you, Brian.
It was great. There's so much. I mean, how do you get at that epic deterioration data? Do you need special permission to get at that data? I mean, how does that work?
Oh, the epic deterioration index model.
Yeah.
So epic embedded in their system. So that's something that's already accessible for Michigan Medicine. It's just running on the back end, not showing on the screen. Yeah, but it's accessible. Yeah. But what's mysterious is that Epic does not provide details about how they develop this model. And
right.
That's why we call it a proprietary deterioration index. So the only thing we can do here is to validate it on the cohort we are interested in, and see if this model can be used for other purposes and how appropriate it is. Yeah.
Yeah, thanks. And so is that they run that every 15 minutes against every patient in the system?
Yes. Yes.
Oh, that's very interesting.
They have different models. As far as I know, there's another model called sepsis model. It's also run every 15 minutes on the back end. So if physicians, they want this kind of information, they can use this model, risk model, to do some research. Yeah.
Yeah, with the sepsis, and that's related to the COVID too. So if these guys get into a, ventilator or something like that, get bacterial pneumonia as a secondary infection, I mean, they often get sepsis, and this is what really could kill them, with the lung involvement. So, it's just like, I was just wondering about the sampling rate. I mean, so I guess what it does is that every patient in the system is looked at in some kind of aggregate form every 15 minutes, and then tries to make adjustments as new data is entered by physicians or medical devices that, tries to make an assessment on the status of the patient. With some things like they move to an ICU or something like that, things kind of go bad. Yeah, it would be interesting to learn about God, so did they publish? I mean, so there's nothing inside. You don't know how it works.
Yeah, so when writing this paper, I was trying to like find some details about this model, and there's just the news articles about how great this model is, but this is not what we really want for a research paper. We want to know the model details. So yeah, we find it interesting just to repurpose this kind of proprietary model. Very interesting experience.
Yeah, thanks so much. This is, yes, it is very interesting. I really appreciate it. It's very exciting work.
Thank you.
Yeah.
Are there any other questions? So Jie, there's a question that just came in to the chat box. I can read that to you. It is,
yeah,
are
sure.
there challenges in identifying actionable versus non-actionable predictors?
So if I'm understanding it correctly, I think the question is asking whether there's something we can tell a predictor is important or not. Is that something you mean? I think for the feature importance, the predictor importance, that depends on the algorithm you are going to use. So here we only talk about the data preparation process. Depending on your machine learning algorithms, some algorithms provide you interpretation of feature importance. And even the algorithm does not provide you the feature importance. I know there are publications of some model agnostic interpretation methods that can help you understand how important a feature is in a machine learning algorithm. Yeah, I hope this answers your question.
Sorry, it was my question. That gets somewhat to it. So you're saying that this model doesn't necessarily tell you which features are the most important as far as ranking, but more so the challenge of what sort of things are actionable as far as in the clinic versus non-actionable things that might be contributing, but a clinician can't, might not have tools to kind of change the patient care.
So
maybe a better way to frame that. Yeah, a better way to frame that might be to what were the kind of actionable, what were the kind of downstream changes in care that are supported by this model, especially in contrast to kind of the holistic of it's taking in a lot of different types of data, but not all of those things are necessarily actionable in the clinic.
Oh, so you're saying like, although we use different kinds of predictors, supply them as predictors in the model, but some of these predictors are not something we can change when we provide intervention. Okay, I see. I think the talk I'm giving today, it mainly focuses on like technical parts, but when talking about actionable, the concept of whether something is actionable, from my talk, I think one thing is that when you design the model, you should carefully design your look back period, look ahead window size. For example, we know if the data is closer to the outcome, the prediction is gonna be perfect. But just think about how far apart your prediction versus outcome should be to provide enough window for clinicians to provide some interventions. I think that's one thing you can think about from the modeling standpoint. And another thing I think is about our runway threshold performance plot is that especially for the PPV, I think this is many clinicians I've interacted with, they care a lot about PPV in a clinical predictive modeling because they want to know like what their burden will be. For example, if the PPV is just like 20%, you have to evaluate 5 patients who got the positive alerts, and you only identified 1 true positive patient, and that can be a lot of burden to physicians, clinicians, and that may be something not actionable for them. And we usually call it alert fatigue in clinical predictive modeling. I think these are 2 things we can consider for whether the model is actionable from our modeling standpoint, but for whether the predictors are actionable, I don't think in my talk we specifically address this, because I think that needs some input from experts like the clinicians. They know better which variables are actionable. Yeah.
Great, thank you so much.
That answers.
Oh yeah, that's
Thank you.
Exactly.
Can I ask a question about the net benefit graph?
Yeah, sure.
So I'm very interested in that graph. It seems like the graph can tell us some information about whether the model should be implemented or not. Can you please give me an example? So for example, what kind of graph, when you see, you would say, okay, this model is okay to implement, and what kind of model that you think it's not it is not efficient to implement?
Great question. So the net benefit, this decision curve is a little bit hard to understand. That's why we are still developing it and clarifying, getting clarification from the original author to understand it completely. So this example graph I am giving here shows a good model, because let's say for the most threshold we can choose here, its net benefit is over intervention for all, over greater than intervention for none, and even for a standard clinical test. So yeah, just comparing their net benefit value. But the authors specifically mentioned that this graph is not for you to pick the threshold. You should pick your threshold first. Say, I want to use a threshold of 10%, and then compare all these lines here and see if the model, if your developed model is the best, has the best performance, has the best net benefits, then that's a proof your model is superior to all other methods.
So how does the net benefit calculated for the model?
So if you're interested, you can search Andrew Vicker's decision curve paper, and it has strict mathematical formulation. Basically, it is a balance of cost and benefits you would evaluate in the clinical practice.
Cool, thank you so much. Can you please put that maybe in the chat?
Yes, at the end of talk, I can put it in the chat.
Sure, thank you. Thank you.
Sure, thank you.
Great, does anyone else have any questions? Well, I'm not seeing anything else in the chat box, and I'm not hearing anybody else unmute themselves. So I'd like to thank Jie for her excellent presentation today. And next week, we'll be hearing from Stephen Lindsley from Indika Rajapakse's lab. So hopefully everyone can join us. And thank you all for coming today.